Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This topic is actually treatable in a trig class anytime after you have actually done graphs of trig functions, because that's all that's really needed here other than knowing how trigonometric functions work. We're going to talk about models, specifically harmonic motion. Models for harmonic motion, that is. So let's talk about what harmonic motion truly is. So simple harmonic motion is just kind of thought of if you attach a mass to a spring or something like that, and you go ahead and pull that spring down and let go. Simple harmonic motion is what would happen to that mass after you let go. It would just oscillate back and forth between the top, the complete compression, and the complete extension. And this ends up being or following what we would call sinusoidal motion. Now, it's not very realistic because obviously as time goes on, this oscillation would slow down, but at least we could see, let me rewind it. If we go ahead and map it out, you could see that it actually is following sinusoidal motion. In fact, in this case, I'm just showing that it follows cosine motion, but it's still sinusoidal motion. Now, again, as I said, this is not exactly realistic because the oscillations would dampen over time. But for right now, let's pretend as though we have something in simple harmonic motion, some object that's just oscillating back and forth between a maximum and a minimum forever and ever and ever. Again, in that case, we call this simple harmonic motion, and here's the definition of it. If the equation describing the displacement of an object at time t is given by the following possible two types of sinusoidal equations, which is a sine of omega, that's what that W is a Greek letter omega. So either we have a sine of omega t or y equals a cosine of omega t, then the object is said to be in simple harmonic motion. In this case, the amplitude is the absolute value of a, just like what we're used to with graphing. The amplitude is just a, or absolute value. The period is again the same as what we've always known the period to be, which is 2 pi over the coefficient of our independent variable. Normally we would call this bx, and then we know that the period of that function would be 2 pi over b. But in this case, when it comes to the physical modeling of the displacement of an object, it is actually considered to be standard notation to have the omega t. That's all. And it's t because with respect to time. That's why we use t for this variable. The frequency, by the way, is just the reciprocal of the period. Again, this is something we've already been introduced to in this video series, but just in case you're picking up in the middle of my video series, there you go. You have everything kind of handed to you here. Now, when I say simple harmonic motion is not realistic, well, that's not actually true, because you can have oscillating things that go on forever, like temperatures oscillate forever, or circadian rhythms, or shoreline amplitude for wave amplitudes and stuff like that. So those do oscillate without dampening forever. And so this is a somewhat trivial but decent example of simple harmonic motion. A cork floating in a lake is bobbing in simple harmonic motion. Its displacement above the bottom of the lake is modeled by this given function, where y is measured in meters and t is measured in minutes. So you have some cork that's rising and falling and rising and falling. By the way, that is not how a cosine function or a sine function looks, but Anyhow, that kind of gives you the idea of it. Find the frequency of the motion of the cork. And I want to start there. We'll focus on that for a little bit because frequency is such an important topic within at least trigonometry and pre-calculus and signal processing, that it's very important for us to spend a few moments talking about what it means. Now, mathematically, we were told frequency is the reciprocal of the period. So I could say frequency is just equal to 1 over the period. And so we could spend a moment finding the period of this function using our mechanical mathematics, right? So we know the period is 2 pi over b. Now I know what you're saying. You're saying, wait a second, you called it omega. Well, I prefer to live in the world of mathematics. And in mathematics, I like to simplify the amount of notation that we learn. And so for me, this is not omega t. This is a cosine of bt plus d. That's just the way I like to write it. It doesn't matter what letter you call it. You call it happy face for all I care. It's still 2 pi over the coefficient of t. So, period is 2 pi over that coefficient of t, which is 20 pi. And that reduces down to 1/10. And that means the frequency is the reciprocal of that. That is, the frequency is 10. But what does that mean? What does it mean that the frequency of the motion is 10? Well, period is number of minutes per cycle. That's really what a frequency is how many minutes it takes, a period. It's how many minutes it takes to have one full cycle of your oscillation. And I say minutes here because that's the unit of time that we're talking about. So minutes per cycle. So the period is 1/10. That means we get 1/10 of a minute per cycle. Well, that means you can kind of think of 6 seconds per cycle. The frequency being the reciprocal of that is going to be cycles per minute. That's really what this means. So 10 cycles per minute. It's number of cycles per unit time is really what it is. So we know that this cork goes through 10 full cycles of this cosine every minute. So it's kind of bobbing up and down, not very quickly, but quickly enough to go through 10 cycles every minute. All right, so let's go ahead and look at the next question, which is sketch the graph. Well, that's not too bad. Again, I'm going to rely on the fact that we were given a function y equals 0.2 cosine of 20 pi t plus 8, and I'm just going to label those pieces A, B, and D. So the amplitude of this cosine function is the absolute value of that lead, or the coefficient on cosine, which is 0.2. So the amplitude is a 0.2. And then we know the period of a trigonometric function is 2 pi over b, which we've already calculated, so I don't need to actually do very much with that. That's just 1/10. And then for me, graphing, I always do a step size here. The step size just gives me my key points. And if you don't know what that is, you're welcome to watch one of my videos on graphing trigonometric functions. But it is the period over 4. That's true for sine, cosine, secant, and cosecant. It's going to be the period over 4. So that's 1/10 over 4, or 1/40th. It's a step size. Then we would have a phase shift. I'll actually write that in. Phase shift. And that would exist if we had some type of, let me zoom in here and say, if we had some type of C in there that we're adding on the inside of we're adding to our argument. If there was a plus C added to our argument on the inside here, then we'd have a phase shift, but we don't. So the phase shift is 0. And then finally, we have a vertical shift, and that vertical shift is 8, because that's how far up or down it's been shifted. Vertical shift equals 8. And now I can actually graph this. I'll start by graphing the midline. And that occurs at a height of 8. And then so that takes care of that. Then I'll plot the phase shift, which occurs at 0. And then I'll plot actually, really what I really want to do is, I could plot that. Yeah, why not? I'll plot the phase shift, and then I'll plot the step sizes. So I'll do 4 steps, 1, 2, 3, and 4. And each time I take a step, I'll step by the size of 1/40th. So there's 1/40th, there's 2/40ths, there's 3/40ths, and there's 4/40. That full length, by the way, is a length of 1/10, which is the actual period of the function. And then I'll go ahead and graph the function. It's a positive, where is it? Right up there. It's a positive cosine. So I'll go ahead and graph the positive cosine here. I'll plot a point up here. It'll cross through right there. It'll go down to here, cross through right there, and go up to here. And I'll connect those dots with a nice, smooth curve. There we go. That's actually not too bad. Once I'm done with that, then I'll graph in the y-axis, and the y-axis just occurs at x equals 0, so I'll graph that in. There's my y-axis right there, and let's see if we really want to label it y. Yeah, they had us call it y, so we're going to call it y. We'll label these maximums and minimums. Remember, they vary from the midline, which is at 8, by the amplitude, which is 0.2. So it's 8 plus a 0.2, or in other words, 8.2 is the maximum, and 8 minus a 0.2, which is 7.8, would be the minimum. Otherwise, we would then somehow, some way down here, graph the x-axis, or the t-axis, I guess. And because it's going to curve far, far down as far as the size of or the scale of our graph, I'll break this. This just means I'm just compressing the y-axis there so that I can fit this all in. And there is my axis. So there's the t-axis right there. And that is a beautiful graph of my function. And if you can imagine it, that 8 just stands for the standard or the level amount of water. So that's when that's the actual height of the pond, the depth of the pond, I guess you could say, is 8 meters. And then due to a wake or the waves, the cork bobs up and down by 0.2 meters. So it's a pretty significant bobbing, actually. Let's see what else we need to do. Find the maximum displacement of the cork above the lake bottom. Well, the maximum displacement, like what's the furthest it will get away from the lake bottom? Well, that's 8.2 meters. We can easily see that. So that would be the answer to that last question, 8.2. Again, that's in meters. So we have successfully gone through and done a full, simple harmonic motion problem. And really, most students understand this. When they see this, they say, oh, you're just having me graph a regular cosine function or a sine function. And the answer to that is, or not the answer, but the statement in response to that is, yeah, that's exactly right. That's all we're really talking about. It's nothing new here. Our next example is going to have us work with a mass suspended from a spring. Same idea, actually, as the previous example. And the physics drawing of this typically looks as follows, where you have a block attached to a ceiling, and then you have some type of spring that hangs down. You have a natural length to this spring that we would call L. L is a natural length. And then it would have a compressed length and an extended length. So when you compress it, it might compress, let's just say that distance. So that might be the compressed spring, and so compressed. And then the extended or stretched spring might go all the way to here. So again, that would be the extended. And by the way, my drawings are always pretty terrible in these situations, but the idea is the same. So there's a compression, an extension, and let's say you extend it, and then you let go, it'll oscillate back and forth. And in fact, it'll be a smooth oscillation back and forth. So it looks something like that. Now I'm going to erase my terrible green and red drawings there because I don't want you to laugh at me. But suppose that we have this spring and we attach a mass to it. Okay. And we pull it down 2 feet. So we attach a mass. Let's just say that after the mass is attached, this becomes the natural length of the spring. And then we decide, I'm going to go ahead and pull it down, 2 feet from its resting position. So we'll pull it down another ... Let's just say to here, another 2 feet. So this is a 2 foot extension. Okay. The mass is released at time 0 and allowed to oscillate. If the mass returns back to this position after 1 second, find the equation that describes the motion. Now, I do want to mention something that differs between textbooks here. If you're in a physics course, it is actually pretty much general or standard accepted notation that down is considered positive and up is considered negative. However, the textbook that I use, which is the Stewart pre-calculus textbook, he does it upside down. And so I think it's just because he's trying to get students used to the sinusoidal motion. So he doesn't want to muddy the waters by telling you the direction downward is actually positive and the direction upward is negative. So let's just follow that author's notation for now, and then I'll tell you how to rectify that if you're in a different course where your author does it properly, where this way is positive and this way is negative. Okay? But for now, let's just pretend as though this way is down and this way is up. So we pull the spring down to here and we let go. What's going to happen, we know, is it's going to do this because it oscillates with simple harmonic motion. At least that's what we're told. Okay. And, well, actually, that's what we're going to assume. Okay. And we're told that actually gets back to this downward position after 1 second. The reason why they tell us that is so that we can tell the period of this function. The period of the function, which is how long it takes to go through one cycle, is 1 second. That's why they tell us that. So the period here is equal to 1 second, technically, per cycle. Okay. And we know that the relationship between the period and the coefficient of t in our function is 2 pi over that coefficient. So let's go ahead and start modeling this. If you take a look at this function here, it looks like an upside down cosine function, and it sure enough is. So let me draw in the midline so you can believe me on this. So there's the midline, and here's time 0. So it totally looks like an upside down cosine. So I know the base function is going to be some amplitude, but it's going to be negative, times the cosine of some bt plus c plus d. Obviously, there is no phase shift because we're starting with full extension at time 0. So our phase shift is actually nothing. We don't have that. And you don't really worry about d when you're doing spring oscillations. In other words, I don't know how many feet off the ground this block is mounted here. And so we just don't really care about that d. It's just, all we're concerned about is what is the model for the motion. So let's go ahead and talk about that. Again, period is 1, but the period we know is supposed to be 2 pi over b. That means that 1 should be 2 pi over b, or in other words, b is equal to 2 pi. That was supposed to be an equal sign, but it just got a little bit messed up there. So I know that this b in this equation that models, that is being built to model the motion, is going to be 2 pi. So that's negative a times the cosine of 2 pi t. Now I just need to know what the amplitude is. Now, if you remember, the amplitude is the distance between the midline and the maximums or the minimums. This distance basically right here. And we were initially told we pulled the spring down 2 feet. So our amplitude is 2. That's the distance between the maximums and the minimums. So this function would be a negative 2 cosine of 2 pi t. And that is our equation of motion right there. Now, I do want to, again, modify this if you're in a course or using a textbook that actually appropriately does amplitude, oscillating or simple harmonic motion. The truth is, when you're working in any course beyond this, or if you're in any a textbook other than one I'm currently using, they will likely label this direction as positive and compression as negative. If that's the case, it'll just be a negative times this function. So in that case, I'll write it in blue off to the side here. The oscillatory motion would be given by this. Y equals a positive 2 cosine of 2 pi t. It's basically the same function, it's just been flipped. And so, and that's because they would consider this direction again to be positive. And if you tilt your head upside down and notice that's the positive direction, then you're actually starting with a positive cosine, and then it tips negative, and then it becomes positive, and so on and so forth. So just a heads up, that's the one weakness of the book that I use, is that it goes the wrong direction from what most physicists would actually work with. So both are technically close to correct. They both model the oscillatory motion. It's just that if you're working with an online homework system or something like that, and you try the negative and it gets it wrong, it's likely coded to accept the positive. And why not do one last example? Circadian rhythms are biological processes that oscillate with a period of approximately 24 hours. So I'm going to write that down actually. So the period they've told us is roughly 24 hours. So I'm just going to say is equal to 24. And that's hours per cycle. It takes 24 hours for a full complete cycle. Okay. Which tells me that I haven't even read the rest of the problem, but it tells me that this coefficient of t right here, it's going to be related to that 24 via the formula period is equal to 2 pi over that omega. Normally I would call that a b, but whatever. So if you multiply both sides by omega, you get 2 pi over 24. So therefore omega is pi over 12. I immediately know that without reading any further that that's what omega is going to be. So anyhow, back to reading. So second sentence, that is a circadian rhythm. Circadian rhythm is an internal daily biological clock. Blood pressure appears to follow such a rhythm. For a particular individual, the average resting blood pressure varies from a maximum of 100 millimeters hemoglobin, I think that's what that means, at 2 p.m. to a minimum of 80 millimeters of hemoglobin at 2 a.m. That's 12 hours later. Find a sine function of the form blah that models the blood pressure at time t, measured in hours from midnight. So t is the number of hours from midnight. That's going to be kind of a critical detail here. Now it would be really nice to actually plot a few points. So I'm going to use this as my midline. I know that at 2 a.m., I'll just say that it's 2 a.m. We have a minimum of 80, and at 2 p.m., 12 hours later, we have a maximum of 100. Well, what's halfway between 100 and 80? If you said 90, you're absolutely correct. So again, this height right here is 100. This depth right here is 80. So those are the low, and halfway in between, it's probably crossing. So something like this. Okay. And then, whoops, that's probably not the best graph right there. Now I'm looking at that, it looks like I've actually reached a maximum prior. So let me just do this. So it looks something like this. It's not the best graph in the world, but whatever. And so that's actually half the period, right? Because we still have all that to go. But right now we know where the midline is, so we can figure out what the amplitude is. The amplitude is this distance between maximum and the midline. So the amplitude is 10. And we also know it's some type of sinusoidal function lifted up 90 units. So I know that D is 90, and I know that the absolute value of A, which is the amplitude, is 10. So far, we've actually kind of put together a pretty decent idea of what all of our variables are, or what our parameters are, I should say. The only other thing we really truthfully need is that C, the phase shift. And the phase shift means a couple things here. I would probably look at it this way, because they're trying to get me to model it using the sine function. So let's go ahead and say it starts right here, because that's where a sine function looks to have started, right? So what time is this? The halfway point between 2 a.m. and 2 p.m. Well, that's 6 hours away from 2 a.m. or 8 a.m. Now remember, T is measured from hours from midnight. So time 0 is somewhere here. This is time 2. So this must be time 8. And this must be time 14. There we go. Now this is unique if you've been watching my videos and kind of watching my lectures. You have not seen me do something like what I'm about to do. But when I teach graphing, I don't teach it with this already pre-factored. I teach graphing with this unfactored. However, if it is pre-factored, then you're kind of lucky, because this statement here tells me where I'm starting my graph. If you have it pre-factored where it's some omega times a quantity t minus c, well then c is the phase shift. If you don't like that, and you want to multiply it out, you're more than welcome to do that. If you want to multiply it out and ignore everything I just said and say that's a sine of omega t minus omega c plus d, that's perfectly fine, because we know that the phase shift where we start graphing is going to be the opposite of that. So the opposite of negative omega c divided by omega. And you'll see the omegas cancel and it'll be c. So that's perfectly fine, but I'm just letting you know right now that c is going to be where we start graphing our phase shift. So where we started graphing the sine function, it's critical to note. So where did we start graphing the sine function? Well, we started graphing it really right there. So at time 8. So in this case, c is equal to 8. That's where the sine curve started where we started graphing the sine curve. The right side up sine curve, that is. Since it's right side up, I happen to know that a is positive and it's 10. We have sine of omega, we've already found to be pi over 12. T minus, we found that the phase shift is 8. And then plus d, and d was 90. That is a model for the blood pressure at any given moment throughout the day. It's not going to be super accurate, but accurate enough to get away with it. All right. Again, I should just mention that when you're graphing the way that I normally graph, I would say this is a sine of b t plus c plus d. But they pre-factored here, and that's why the phase shift is not negative c over b. It is actually just the value of c, because they pre-factored that so that we had that ready to go. Okay. This is also, think of it this way, it's from your transformations from algebra. There you go. That's another way you can think about it. All right, so this is pretty much how simple harmonic motion problems work. Either find formulas or graph formulas, or state period or state frequency. That's it.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.